Okay, so we can start. Any questions so far? So as I said, today we are going to talk a little bit. Entering the harder part of the course, I think. Which is this thing about vector spaces. Um, it is not too bad, but still a bit more abstract than what we did until now. So let me give you a crash course on vector spaces first. So what's a vector space? So essentially, we have been using the word vector, right? Which we thought about this like in terms of these arrows. So like a vector space, essentially like an abstraction of that idea, and it ends up being anything where you can add the elements. Okay, let me say it a different way. What's thing you can do with vectors? If you think of a vector as an arrow, you can add them together, right? You can add vectors. How did we add vectors? We added their entries, right, one by one. First entry with first entry, second entry with second entry, etc. And another thing we did with vectors is that we could multiply a vector by a number, right? And if you remember, that just rescales the vector. So essentially, the idea of a vector space is that we will call a vector space like any collection of objects where we can do those two things. So a vector space is just a, a set. Not sure how familiar you are with a set, but the word set, but by set, I just mean like a collection of objects. Don't read too much into that word. So where two things happen. The first one is that you can add elements of this set to get a new element of this set. So you can add elements of this set to get a new one, to get a new element of the set. And also you can multiply an element of the set by a number, by a real number, and still get a new, and you still get a new element of the set. So I'm about to give you a bunch of examples so that you see what I mean, but you can multiply an element of the set by a number, by a scalar, let's call it, you get a new element of the set. And you get another element of the set. Okay, so let me give you a couple of examples. so that this doesn't look so weird. Here's a few examples. So the first one is just the one that we have been using a lot, which is the Cartesian plane. This is called R2. I don't know if I have used that notation before, but what I mean by this is that an element here is just an ordered pair. Okay, so in pictures, the Cartesian plane is what I'm calling now R2. That's kind of like the standard convention. So this represents all possible order pairs that you could ever think of. So it represents like all the points on the Cartesian plane, essentially. That's what this notation means. And so the idea is that this is what I'm trying to say is that this is a vector space, and what makes it a vector space? Well, two properties. That if you take two elements here, right? I don't know what's happening with this cable today. If you take two elements here, you can add them together, right? So let's think, what is an element in this collection? It's just an ordered pair, so you can call it x1 and x1, y1, right? And what is the second element? You call it x2, y2, right? And so if you add them together, well, we had talked about how to add vectors, right? It's x1 plus x2, y1 plus y2. And you see, this is a new vector. So it's kind of any sum you can think of continues to remain on that collection. So this is a new vector or a new element of R2. And if you take your favorite number, right, and you multiply it by, imagine that this is like a real number or a scalar, and you multiply it by a vector, by an element here, it's like y, so it becomes 3x ky, and that's just another vector. So this is another element. Yeah.
The new element is already inside here.
Right, it has to exist already in this collection, right? So in fact, it's always useful to do like an example and then a non-example. So to see what's the difference. So let's do a non-example so that you see what it's better to just to get like a sense of what's going on here. So let me give you a non-example, which would be like the unit circle. Okay. So this one will be a non-example. So the unit circle on the xy plane, right? So by that, I just mean that I would be like taking P to be like the points x, y, such that x squared plus y squared equals 1. Right, so I draw this. Now B is like corresponds to this thing, right? Just the circle itself, the green thing. My claim is that that wouldn't satisfy the definition of a vector space. Okay, there's something that I mean, there are tons of things that go wrong here, but what's a thing that goes wrong? I already erased the properties, but what would be one thing that goes wrong?
If you have the vector 1, 0 and you add it to yourself, it'd be 2, 0.
Right, that's a good example. So we have a vector here, right, which would be 1, 0. Let me put it as a column, just to. So this is why it's not a vector space. Is it not a vector space? So as you were saying, here's an explanation. P, which is 1, 0, right? Is inside B, which kind of looks very confusing because I'm using the same letter. So it's inside the unit circle, right? But if you do B plus B, right? What is B plus B is that's just going to be 2, 0, right? And that is no longer inside the unit circle, right? It's like the operation of adding them together took you outside the circle, right? And this is not in the circle, right? Not an element of the circle. And so but the requirement of a vector space is that if you add two elements inside of it, you should get something that continues to be inside of it. So that's what goes wrong, right? But for a vector space, it should belong to this set. That make sense? I don't know, making so far so good. Okay, so any questions up to this point? Yeah.
Please was the set like just the circle.
Well, the circle with the inside, well, it does because it's an equals. It's just the circle, the outer thing, not the disk. But still, even if it were the disk, it would fail. Essentially, this one also would work, right? For saying why it wouldn't be a vector space, right? But yeah, so either one would not have worked. But here I'm just referring to. I'm not including the inside of the circle in this picture. Any other questions? Okay, let's do some more interesting examples. So, well, just as useful to bring it up explicitly, like you could like instead of putting R2, you could put like R3. What is R? What do I mean by R3? It would just now be triples, right? Like the 2 was replaced with a 3, so it just means like literally all of space, kind of. So like here you have X, Y, Z. Right, yeah, so the elements here are just like triples X, Y, Z. So this is example 3. Oh, sorry, let me write it properly. I mean, that this is a vector space is essentially the same thing that I wrote for R2, right? Like, if you add two together, you have like x1 plus x2, y1 plus y2, z1 plus z2, right? So it's still a new vector. And if you multiply a vector by a number, you kind of multiply each entry, but you get a new vector. So, I mean, the reason why this is a vector space, it is for the same reason that R2 is a vector space. Like there's not really much of a proof. So this R3 is a vector space. Okay. But then there's a inside of R3. Okay, but there you can kind of come up with some more interesting examples which live inside of R3. Let me see, trying to explain what I mean by this. Here's 4. Let's look. Let's call it P. You'll see why. Or W. This is actually the letter. Vector spaces are usually called U, V, and W. I should have said this as a remark. So the letters that. Let me make a remark before keeping with the examples. You know, in the same way in which there's like some usual letters for matrices like A, B, C. The usual letters for vector spaces are U, V, and W. That's like the 3 that you will always see the majority of the time. So the typical letters for vector spaces are U, V, and W, and they're always capitalized. So that kind of also helps you. So that's if you had more in around, you would just call them like U1, U2, U3, V1, V2, V3. Like typically, you don't go beyond those 3 letters for vector spaces. So here's a 4th example. It would be let's call it W. Would be like X, Y, Z. Right, like okay. This is also notation that you may not have seen this before. I'm not sure. This means that this belongs to R3. It means this is like one of these Greek letters, epsilon. But this means belongs. So I'm saying like we're looking at the vectors inside R3, right? That's why it has 3 entries. But I'm not just going. I'm going to give you like an extra condition. And the extra condition that I want is for x plus y plus z to be 0. Right, so now it's not arbitrary. The vectors in this example cannot have arbitrary entries, but rather, right, when you add them together, they must add up to 0. Right, so just to make this clear, negative 1, negative 1, 0, right? If you add their entries together, that gives you 0. So this would belong to W. But like 1, 1, 1 would not belong to W, right? Because their entries add up to 3. The way to say that it does something does not belong is that you put like a vertical line in or a slanted line somewhere in this notation for belonging, since the entries add up to 3, right? Adds to 0, entries add to 0, and so here entries don't add to 0. So here by this I mean does not belong. That making sense? So far, so good. So my claim is that this is actually going to be a vector space on its own right, and we have to check it. So now, before going through this, like, not sure if it's if Yeah. Here, here's a picture for what this looks like. I don't know if anyone can recognize this equation.
It's like.
Right, this is like the equation of a plane for those who have seen this before. So like the way in which this would look like. This actually looks like a plane. This is like the equation for a plane. Passes through the origin, and you'll see this is important later, but. This, so we saw that, for example, circles would not be vector spaces, but at least this particular case of a plane is a vector space. Okay, so that's kind of useful to know. So let's check that it is a vector space. And like there's usually like a question that will give you like the exam or other places where I'll give you like a set like this and ask you, well, check whether this is or not a vector space. So this is one of these typical questions you have to be ready for. That's a very common question. So to check this is a vector space, you have to check these two properties. So imagine that I take x1, y1, z1 in W, right? And x2, y2, z2 in W, right? Like the first thing that I want to check is that there's sum, right? When you add them together, you get something inside of W, right? So what is v1 plus v2? That would be x1 plus x2, y1 plus y2, 1 plus z2. Right. So my question is, does this belong to W again? Right. So, right, I still don't know, but what do I need to check? What's the condition that I need to check for belonging to W? The condition is that when you add up their entries, right, you get something equal to 0. So what we have to do is add up the entries of this vector. So what do we do? X1 plus x2 plus y1 plus y2 plus, let me put parentheses to just indicate which are like the first entry, second entry, third entry. So the question is whether this sum equals 0 or not. If we know that that's 0, the first condition is satisfied. Is that making sense? Right, so this is a very important point. So let me just check if there are any questions. So how do you show that this sum should actually add up to 0? Yes, good. So you just play around with the fact that the sum, you can reaccommodate the terms, right? So right, you can put the first, the ones with the 1 together, and then you can put the ones with the 2 together. That making sense? And this first one is 0 because that's the condition for like the first vector to belong to W, right? So this is 0, since B1 belongs to W. And this one also is 0, since B2 belongs to W. That making sense? And now 0 plus 0 is 0, so we're good to go. Yeah.
Like this, do we have to do like this mathematical like cell explanation, or should we just say two vectors at one plane sum is going to also combine on the same?
Well, I'm going more for something like this because my next example was that it's not that every plane has this property. It is important the fact that this was added up to 0. So for example, I had changed this 0 to a 1, right? Then you would, if you redo this problem, you would do 1 plus 1, which is 2. and that already takes you outside the plane. So it is actually important that the zero was there. So right, but we're not looking. It is yeah. So the expectation is more something along these lines. The proofs are not extremely complicated, but it's more like of a writing type thing where it's kind of important to realize whether this works or not. Is that making sense? But yeah, like the next example I was going to do is actually change this 0 to a 1 so that you see the difference. And then part B is kind of similar, right? I mean, remember there were two properties to check, that the sum kind of always remains inside and that a vector times a number remains inside. So if you take a vector in W, usually part B is a lot faster. You multiply it by a number, right? So I now want to know whether this, my question is this still inside of W, right? And again, the condition for being inside of W is that when you add up their entries, right? You should get 0, but what happens when I add up the entries here? You can just factorize the number Z, right? So you get C times X plus Y plus Z. And so this is C times 0, and then this is 0, so we are fine, right? But yeah, like the style of proof is more or less along these lines, what you're being expected to know how to do. Is that making sense? Yeah.
Is there an example that satisfies A but not B?
Let me see. Yes, I'm sure I can come up with an example. Oh yeah, there. Okay, I'll give you that example in a second. Let me just do the one with 1, and then I'll give 2 more non-examples and then an interesting example. Yeah, this one is kind of that one is also cool to think about. So is it making sense so far so good? I mean, this is actually, I mean, this can be fun because I'll tell you later like some other cool examples that do show up here. But like at least this one is a plane and this does work. Here's another yeah, I'll give you 2 non-examples. Now, so non-example number 2, I think this is the second non-example. Let's call this U or what, something else. Imagine I had put like a 1 here, right? So that's the only difference with the one that I wrote before. Now my claim is that this is not a vector space. Right, and again, for this, you're just free to give an example where the property, either of the 2 properties fail. It's up to you which one you want to choose. So what works here? How can you show this as a vector you can think about inside it is explained. Well, it depends. Oh, you want to go with the property? Yeah, we got like let's do with the sum, but it's kind of the same, right? Like for example, you could take something like this, and it's the same, right? If you multiply this by 3, it no longer is inside, right? So this one belongs to you, but you know, b plus b does not belong to you, right? You can check that because you just get to or nor, like 3 times b belongs to you. So either of these 2 works. It's not that you have to give an example for the failure. It just suffices to find like one of the properties failing. So either of these would have worked. So either works, either explanation works. Does that make sense? Okay. Anyone else? Yeah.
So plane is not doesn't the two vectors are in the plane, so and if we have them written on parallel, that's also that's a different.
Well, the thing is that that's true when the planes are actually centered at the origin. It does, like, if you go through like the thing is like the parallelogram law, I mean, it is it can be confusing because here we're thinking of the vectors are starting from the origin. So when you draw the two vectors, if the plane right, if the plane does not be like you know, like for example, like here, like two vectors on this plane, like this is one, right? And then 1, 0, 0 is also on the plane. And if you add them together, it won't be on the plane. So if you go through the parallelogram law, it actually ends up looking outside, will look it won't be contained in the plane. It kind of takes, I mean, the easiest thing to check visually like that this works, it is okay. I can even draw it. This one I can draw. Like the thing is like how this plane, how this does this look like? It looks like a plane that goes through the points 1, 0. Oh my god. This is X, Y, and Z. 1, 0, 0, 0, 0, 1. 0, 1, 0. And 0, 0, 1. So actually this plane is a plane that contains these three vertices of a triangle. And you know, this is the one I'm calling B, right, in this picture. This one would be U, for example. And if you do V plus U, you see like V plus U will look somewhere in, I mean, it's kind of complicated to look at here. But it's on the XY plane, but it won't be up inside the the plane. Yeah. Is that making sense? It takes a little bit of visualization to see it, but it does need you for the addition to remain in the plane, you do need like a 0 here. Does that make sense? Yeah.
You said that like the vector space that consists of the vector space, is that true for all vector spaces?
Could you repeat the question? What in fact did I say?
All vector spaces have to consist of a smaller vector.
I mean, a vector space, right? So a given vector space like R3 can have smaller vector spaces like this one. And in fact, this one will be called in a couple of minutes a subspace of R3 because it's a vector space on its own right, but it's also containing the smaller one, right? A vector space, you know, can always, like, you know, any vector space, like, essentially can always be thought of like being inside a bigger one just by doing some like dark magic. Like you can take R3 and like you add like a fourth entry equal to 0, and then there you go. Like so you can always like draw like a vector space in a some bigger vector space. It's kind of like I mean, it's good to know you can do it, but it's more interesting going the other way. Like you have a vector space you care about, what are these subspaces? Now I have to give you like this example that where like the sum property works and not the multiplication property. This one is actually cute. And then I'll give another example, and then I'll give you some more definitions. So here's another non-example. Imagine I had taken U, B, the points on the XY plane, where X x is greater or equal to 0 and y is greater or equal to 0. And this one will do the trick. So how does u look like in this case? It looks like the first quadrant, right? Is that making sense? Is it clear that if you add two vectors here, it continues to be in the first quadrant, right? Because if you have two things whose entries are non-negative, if you add them together, their entries continue to be non-negative, but now the multiplication property fails, right? Because, for example, you have like 1 inside of u, but if you multiply this by -2, because you have to be able to multiply by any number that you want, it does not belong here, so this doesn't work, right? So it's not a vector space. That making sense?
If you had like a set that just contains like the ordered pair 0, 0, would that be a vector space? Or?
Yeah, that's a good example. That's called the trivial vector space for like hopefully trivial reasons, but it is, yeah, I should it is the smallest one in a sense, like it's just the one that's the vector 0. Yeah. Maybe I should just say it, right, because you're always allowed to multiply a vector by the number 0. So that means that the vector 0 is always inside any subspace or vector space. So let me make that as, write it down as a fact because it's important. Fact, the vector 0 like for example, 0 is always inside a vector space. It's always an element of any vector space. And the other fact is that if you took V to just be the vector 0, that is a vector space, but like, kind of for very silly reasons. And so this is called the trivial vector space. It's a vector space called the trivial vector space. Right, because if you add two elements here, well, they're the same. So 0 plus 0 is like the vector 0 plus vector 0 is vector 0. A vector 0 times any number is vector 0, right? So it's a vector space of the trivial vector space. Does that make sense? Yeah.
So then you could use that to like say if a vector is a vector space, like if it doesn't.
Correct.
Have 0,
yeah, so in many, like in this example, you could immediately say this is not a vector space because 0, 0, 0 is not here, right? So that's like faster way to check in that it was not a vector space. And sometimes like something may still, like here 0, 0 was inside of it, but still this still feel to be a vector space. So it's what people call like a necessary but not sufficient condition, right? It always has to be inside, but that on its own does not guarantee that we'll make it a vector space. Does that make sense? Any other questions up to this point? Okay, so this is why, so let me give you what I like to call like the grown-up examples. So here's a grown-up example of a vector space. We won't really use it, but it's kind of useful. This is why I asked you if you had seen like when you knew what a derivative is. So if you know what a derivative is, you're good to go. You will understand this example. If not, don't worry too much about this. No, the empty one is not allowed because 0 has to be always inside. So yeah, that one we do not. So here's a grown-up. you have a mass M and you connect it to a spring. So there's like this thing called Hooke's law, right? That gives you the formula for the force that this spring exerts on the mass. Well, I'll write it in without vector notation, but anyone remembers the formula for this spring? Let's say it has like a spring constant. That's the name of that spring constant equal to K. So what?
Yeah.
It's negative kx, but yeah, I mean, except for the sign, yeah, it's correct. Yeah. Okay, but then you use Newton's law, right? Which says that force equals ma. So this gives you ma, right? So for, I mean, again, like if you have seen this, great. Don't worry about it. This won't take too much time. So you get that minus kx equals ma. So far, so good. But what is acceleration in terms of derivatives? Anyone remembers this? It's the second derivative of the position of x with respect to time, right? So this is like m times the second derivative of x with respect to time. And so you kind of can rewrite this equation in a nice, like if you send it to the other side, it kind of makes sense because there's a minus here. So you get like 0 equals m times the second derivative with respect to time plus kx. Is that making sense? So I'm going to be lazy and like I'm going to work with units where both m and k are 1. You know, mass 1 and k1 just for to simplify my life. So because I'm lazy, I'll put k equals 1 and m equals 1. And so the equation, if you do that, I mean, it just simplifies a little bit. The constants look less tedious to see all these constants. Does that make sense? That's Hooke's law. Now, this is saying find a function such that when you add it with the second derivative, you get 0. Anyone knows from Calc 1 a function whose second derivative added to it is 0? Right, if you take sine, so if you take sine, so for example, that's called a solution of a differential equation, by the way. So if you take example, if you take sine of t, right? Again, if you have seen this, dx dt is cosine of t, right? And the y, if you take a second derivative of this, another derivative, the derivative of cosine is minus sine, right? So when you add them together, right? The second derivative plus x gives you minus sine of t plus sine of t, which is just 0. That makes sense? So that means that the function sine solves this equation, right? So there's like a solution where like the thing just like oscillates. Kind of makes sense if like there's a friction and other things, if you have ever seen like done the experiment of putting in like an actual spring. Now my claim is that there you can define a vector space here, which is all the functions that solve this equation. And that would be a vector space. Okay, so that's a grown up example. So the set here is like the functions. So this is like a function which solves Hooke's equation or like the Hooke's law. And that's kind of like the example that you study if you take differential equations like math 244. This is called like a linear differential equation. So like the claim is that this is going to be a vector space. It's important that this is 0 to make it a vector space, analogous to the case of the plane, where if you put like a 1 here or something like that, it wouldn't be 0. It wouldn't be a vector space. So the analog of the plane case is like having like a 0 on this side, basically. I mean, again, like if you take linear differential equations, you would like see all these details, but just to finish the example, let me tell you quickly why this works. So what are the two properties that you would need to check? You would need to check that the sum is contained, right? If you take this, that means is that if you take two functions which have this property, then the sum has this property. So imagine that you have like two functions, x1 of t and x2 of t inside of V. So that means that like the second derivative of x1 plus x1 gives you 0, and the second derivative of x2 plus x2 equals 0. That's like the condition for each of these to be inside. And then when you do the sum, right? What happens if you do the sum? Right. There, how can you get to 0 with the sum with this? What property can you use of the derivative? The sum of the derivative of the sum is the sum of the derivatives. That sometimes I don't know if this they give it a name. Don't remember if they give it a name in Calc 1, but that's called linearity, and this is linear algebra, so it's not a coincidence. So this is called this is the second derivative of x1 plus the second derivative of x2 plus x1 plus x2. And then we do something that we have been doing all this time, right? Which is like we group them. So this one goes with this one, and then this one goes with this one. Right, and then you get and this is gives you 0 from 0, and then you get. So that means that if you take two solutions and you add them together, you get a new solution. And I won't do the other part, but you can check it again, because this type of example won't be used in the course. Anything that involves calculus, we won't do. But then if you want, you can check for yourself that, well, you multiply, you take a solution, a function multiplied by a constant c, then this still solves the equation. That kind of makes sense because you can multiply both sides of the equation by a constant, and doesn't make, a derivative of a constant is 0. I mean, it works because you can move a constant inside or out a derivative. And so you can, if you're curious, you can check this property. But that tells you this is a vector space. Yeah. Right, this is like a name. Yeah. So the fact that if you have two solutions, you can add them together and you get another solution. That's what's called linear superposition. Yeah. Let me get that. There's also, I don't know who has heard like Schrodinger's cat. I mean, so that's kind of how Schrodinger's cat paradox works. I mean, you should watch the Big Bang Theory if you I think it's mentioned in one of those episodes. But the idea is like there's like a analog, like the analog of Newton's law for like an electron or a proton is called like Schrodinger's equation, and it has this property that if you take two solutions, you add them together, and you get a new solution that's called quantum superposition in that case. And like kind of like the paradox is that you could think, well, if you apply that idea to like microscopic objects, like you could have like a solution that represents a cat being alive, and another solution representing like a cat being dead. And then by the superposition principle, there would be like a solution that is like cat dead plus cat alive. And then there's like a whole like literature on how you should interpret like, that case. But yeah, it does have weird content. But yeah, it is like a consequence of like this linearity thing. It's not that equations that are more complicated, but it's okay. So this is like it's useful to know that these concepts apply not only to like concrete things like vectors, but also like solutions, equations, or things like that. That's kind of what makes the linear algebra thing interesting. Okay, so just finished. I already gave you a bunch of examples. So hopefully now you have like a feeling for what these vector spaces are. So just to continue with a little bit of definitions, what's a subspace? It's a vector space that just sits inside a bigger one. That's not a big thing. So here's another definition. A subspace. So a subspace of a vector space D is just a set, I mean, it's just a subset it's a subset of B that happens to be a vector space on its own right, which happens to be a vector space. So, for example, B, I think that I call it W, W, which was like the plain thing. This thing that we had seen that it was a vector space, you can also call it like a subspace of R3 because it is a smaller part of all of R3, right? A subset of it.
Does a subspace have to be a proper subset or can?
And it is allowed the silicase where it's itself. So you can call like a vector, like you could call like a R3, like a subspace of R3. Because it's more like a lesser equal, like yeah, that's right. You're taking this logic class. This is where you think about these things. Yeah, yeah. So the extreme cases are allowed where like you can be a subset of yourself. Or a subspace of yourself. Obviously, like in practice, like if I ask you to check that something is a subspace, I'll give you something more interesting than just like, the actual space. But yeah, those possibilities can arise. And the trivial subspace is always a subspace of anything, right? Like that you could think of. So another example is that it's always a subspace of a vector space. That makes sense. Um, and B is always a subspace of itself. But yeah, I don't like this. I mean, it is a subspace of itself. I mean, this one is less important because, but it is kind of like a consequence of the definitions, like of how, like, what do you mean by inclusion? Is that okay? Any other questions? Okay. All our examples would be like subspaces of like R2 or R3 or R4. So like that's kind of what we're going to be focused on this class. Let's see, I'm trying to check how to introduce. Okay, so now we come to one of these confusing confusing, I mean, very important concepts, which is called a basis for a vector space. This is one of the key concepts of all of linear algebra. I'm just trying to see if I have enough time to, I mean, if not, I'll just give you half of the story today and next time we'll finish it. But so here's what a basis of a vector space is. Okay, so this is like, again, one of the top three definitions of all the course. So so you have a vector, and this can be, again, a bit tricky, so I'll give you a couple of examples right after giving you this definition. But so we say that, let's see which letter I'm using in the notes. Yeah. What's the notation? Okay, yeah, that's so here we have k vectors, v1, v2, v3. So here is like what I'm trying to say here is that I have k vectors. These are a basis, or they form a basis of a vector space. If two things are satisfied. Okay, if two things are satisfied. So the first thing is that if you take any random vector, you can write it in terms of the basis as a linear combination. I don't know if you remember this linear combination business, but this is where it becomes really important. So the first property is that any random vector of V, let's call it vector space V. Any vector V can be expressed in terms of the basis as a linear combination. Can be written, and again, I'll do this very concretely in a second. Can be written as a linear combination of the basis vectors. So you can find, anyone remembers what was the definition of linear combination? I mentioned this not too much, like didn't spend too much energy describing it, so I'm not sure thing.
It can be read as like a sum of conflict.
Yeah, so the idea is that you can find constants or scalars C1, C2, up to CK, so that V is C1 V1 plus C2 V2 plus C3 V3 plus CK. I'll give you an example again what I mean by this in a second. And the other condition that will make this a basis is that kind of this collection is as small as possible. And by that, I mean the vectors, these vectors are linearly independent. Again, which is like something I briefly mentioned before. So let me remind you what that means. B1, B2, up to Bk are linearly independent. Which for us, I mean, that there's kind of like a definition that that you can always apply that works, but I'll give you, put it in a way that's like the one that you need to think about for the course. The way that like this meant, this means that the homogeneous system for us, right, for us, this means that the homogeneous system AX equals 0 has only the solution, which is a trivial one. If you remember, like a homogeneous system always had at least one solution, or infinitely many. So I'm saying the thing that will make this linearly independent is that there's only the trivial solution. Has X equals 0 as the only solution. So again, this is kind of like the most one of the like most abstract parts of all the course. So let me give you some examples so that you see what I mean by this. And this is like in practice how you do this. Okay. So let's think about R2. Just the easiest example where this kind of can be applied in an interesting way. So you choose your favorite random vector in the world, let's call it V, right? Okay. And the idea of finding the basis is to express any random vector in terms of just like a given number of vectors. So here, what I want to do, my claim is that I should be able, you'll see why next time. But what I want to say is that I can express this vector in terms of just two vectors. Anyway, and in the sense that I can write this vector as a sum of these two vectors. Which two vectors should I try?
0, 1.
Yes, like, is that the one that you were going to say? Yeah, is that everyone? Correct. So you have you have this vector which I had called E1 before, also called I, and the physics courses. And this vector, which I had called E2 before. So my claim is that E1, E2 make a basis for this vector space for R2. So E1, E2 form a basis. So just to give you like a proof of how this works, like first, like let me give you an example. Like imagine that I gave you the vector 3, 5, right? How can I express this as a linear combination, as a sum of E1 and E2? How will you write it?
3 times E1 plus 5 times E2.
So this is like the linear combination property I'm talking about. Is that making sense? And then if it had not been 3, 5, but XY, right? If this is like just XY, like what should this be equal to? It's just X E1 plus Y E2, right? So this is like this is saying that an arbitrary vector, right, is the vector E1 times a constant plus the vector E2 times a constant. This is the linear combination property. So this is verifying property 1 for the claim that this is a basis. So this is like the proof. I mean, it looks very silly, but that's literally the proof of showing that this is everything makes a linear combination. Does that make sense? And then we have to check property 2. Actually, so this is part 1. Okay. Property 2 is to check that they are linearly independent, right? Again, the way in which you have to think about linearly independent in this course, there are other ways to think about it, but I'm giving you like the most concrete way for your purposes, is that you make a matrix whose columns are these vectors, right? So you make a matrix A, which is like E1, E2. And now you have to study the homogeneous system, okay? So you have to study, study 1, 0, 0, 1 times xy equals 0. And what you have to show is that this forces x and y to be both 0. Well, like this case is kind of like the point of this, like this claim is verified the moment that you say that this forces the solution to be the trivial one, right? So why? I mean, there's so many ways to do this, like, but why is the solution to that homogeneous system unique? That's my question. Why is this the solution to this homogeneous system? I mean, there's right, like it's already reduced. There's nothing else to do. The nullity is 0. I mean, you can also just rewrite what this means, right? This means that if you do the matrix multiplication, this means that x equals 0 and forces x to be 0 and y to be 0, right? Like it gave you no more choices. So this is like a unique solution, right? So you're done. Is that making sense? I mean, like again, we have to do tons of examples of this so that it sinks in. So next time, what I'll do is like do a few more which show that certain things are particular basis, because it's kind of like this is one of the most important things of all the course. Like, okay. So far, so good.
You also show for linear.
Yeah, you could also have said that the determinant that this matrix is invertible. So because it's invertible, it has a unique solution. That's a good other alternative. Or there are tons of different ways to say it, or also can say that this matrix is invertible. Okay, that making sense. So again, next time what I'll do is just give you a bunch of examples of vector spaces, finding bases, etc., etc. The fact, I mean, the cool thing that I mean, this is one of the important theorems of linear algebra. The fact that we needed two vectors here to get a basis means that the dimension of this vector space is 2, but I'll tell you about that later. And no other basis you can find, any other basis you could find for this, I'll give you other examples of bases for R2, would have dimension 2. Okay, so there will be something called the dimension of a vector space, which is one of the most important like properties of it. Okay, and just to finish today, because we don't have that much time. So if you go back to like the Cook example, just to close this chapter down, like I will mention this again. What you prove in like in differential equations is that it has a basis formed by two solutions, by two functions. X1, which is sine of t. We saw that sine of t was a solution, right? And x2 is cosine of t. And what you show in differential equations is that this form a basis of this vector space. So any other solution is a linear combination of sine and cosine. So the solution, like in Cook's problem, is that like general solution is that any other function that solves this equation is something times sine plus something times cosine, which physicists usually write it like a cosine of omega t plus t, where this is like an amplitude and this is a phase displacement. They kind of do like a trick, but you can always rewrite it this other way. So this form a basis. So any solution is any other vector, right? Is a linear combination of these two. Any other vector can be written as. Oh, sorry, maybe I put sign first. So. Okay. And again, we won't really go into that, but it kind of shows you that this concept of basis is very important because it does appear like once you find like a basis for a vector space, then essentially you kind of know everything you could ever ask for about. I mean, anything you want to know is already out there because like the basis will determine anything else. There's this thing called like Fourier analysis where you process signals, and the basis is kind of like an analog of these sines and cosines. And the idea is that you take a signal and you decompose it in terms of sines and cosines as a linear combination. It's an infinite linear combination, so you need like a series, but more or less everything else is kind of the same. And that's kind of like who you compress images and other things. Like linear algebra is kind of like anytime you want to break something into elementary pieces, like you kind of think about it from this perspective, and if there's some linearity involved, then linear algebra is really okay. So yeah, next time what we'll do next week, I'll tell you a bunch of examples about bases, how to find them, etc., etc., and then we'll talk about the dimension, and then the important stuff, vector spaces associated to a matrix, which is like the cool part of the course. Okay, so I'll see you. Yeah.